Welcome back to Gungahlin College Maths Applications video lecture series. In today's lecture, what I'd like to do is continue where we left off with matrix multiplication. So I'd like to answer the question, if we have two matrices and we try to multiply them, so A times B, is this the same thing as multiplying B times A? So does the order of multiplication matter? So the way that I'd like to answer this question is basically just to do an example. What I'd like to do is multiply e.g. 1. Do an example of multiplying a 2 by 2 matrix by another 2 by 2 matrix. So let's pick the 2 by 2 matrix, 1, -7, 2, 0, and multiply this by the matrix B, -1, 3, 4, 2. So what I'm going to do is first of all multiply A times B, and then I'm going to switch it around and multiply B times A and find out whether or not they're equal to each other. So first of all, A times B. A times B is 1, -2, 2, 0, times -1, 4, 2, 3. So I'm going to do this multiplication a little bit more quickly than we did it in the last video lecture, just because I think you guys are getting used to this and I'd like to try to save a little bit of time. So 1 times -1 plus -2 times -2, 1 times 4 plus -2 times 3. Row 2 times column 1 is 2 times -1 plus 0 times 2. Row 2 times column 2 is going to be 2 times 4 plus 0 times 3. So let's simplify this out. 1 times -1 is -1, plus -2 times 2 is a -4, so that's a -4. 1 times 4 is 4. -2 times 3 is -6, so 4 minus 6. 2 times -1 is -2, plus 0 times 2 is plus 0. 2 times 4 is 8, plus 0 times 3 is 0. So again, simplifying, -1 times -4 is -5. 4 minus 6 is -2. -2 plus 0 is -2. And 8 plus 0 is 8. Alright, so that's A times B. Now what I'm going to do is multiply it the other way around, so B times A. So B times A is -1, 4, 2, 3, times 1, -2, 2, 0. So again, row 1 times column 1 is going to be -1 times 1 plus 4 times 2. Row 1 column 2 is going to be -1 times -2 is positive 2 plus 4 times 0. Row 2 column 1 is going to be 2 times 1 plus 3 times 2. Row 2 column 2 is going to be 2 times -2 plus 3 times 0. So simplifying this, we get -1 plus 8, 2 plus 0, 2 plus 6, and -4 plus 0. So this simplifies to 7, 2, 8, 0. So A times B was -5, -2, -2, 8, and B times A was 7, 2, 8, 0. So it's quite obvious in this example that A times B is not equal to B times A. So this is in general, actually. So in general, if you pick two matrices and multiply them A times B, and then turn around and multiply them the other way around, you'll get a different answer. So the way that we say this is we say that matrices don't commute. And what this really means is that when you write two matrices, A and B, it's not the same thing as B times A. So we can't just switch the order around and get the same thing. So matrices don't commute. So that's in general. Now, there are some exceptions to this rule. One exception that we're going to talk about today is probably the most important one. So there's basically a very special matrix called the identity matrix. And it's pretty much exactly like the same thing as multiplying a scalar, so just a number, by the number 1. What it does is it gives you back the same matrix. So any matrix A times the identity matrix equals that matrix A again. The identity matrix, this is important that we do it both ways, I times A is also equal to A, right? So in this case, A and the identity matrix do commute, right? A times I is equal to I times A, and both of these are just equal to A. So we're only going to talk about the identity matrix when A is a square matrix. So what I'd like to do is basically try to talk about this as concretely as possible. So I just want to give you an example of what the identity matrix actually looks like. So when A is a 2 by 2 matrix, all right, so the identity matrix is going to be different depending on how big A is. When A is a 2 by 2 matrix, the identity matrix looks like this: 1, 0, 0, 1. When A is a 3 by 3 matrix, the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. When A is a 4 by 4 matrix, you can probably guess, right? It's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Right, so one way of saying this is the identity matrix has ones on the diagonal, right? So as you go down across from one corner to the other corner, there are ones all along that diagonal and zeros everywhere else. So you could write out any identity matrix. So when A was an n by n matrix, you could now write what the identity matrix is. It would have ones along the diagonal and zeros everywhere else. So what I'd like to do now is basically an example. So I'd like to show you exactly why the identity matrix is the identity matrix. So what I'm going to do is pick a matrix A, 1, 2, 3, 4, and then I'm going to multiply A times I, and then I'm going to turn around and multiply I times A, and hopefully in both cases I'll get the original matrix back. So because A is a 2 by 2 matrix, the identity matrix is going to be this one here, 1, 0, 0, 1. So A times I is 1, 2, 3, 4 times 1, 0, 0, 1. So let's do this multiplication. So row 1 times column 1 is going to be 1 times 1 plus 2 times 0. Row 1 column 2 is going to be 1 times 0 plus 2 times 1. Row 2 column 1 is going to be 3 times 1 plus 4 times 0, and row 2 column 1 is 3 times 0 plus 4 times 1. Alright, so let's do it the other way around now. Oh, hold on, I haven't actually simplified this. So let's simplify. Anything multiplied by 0 is just 0, so I'm just going to go ahead and cross these out. So this is equal to 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, 4 times 1 is 4. So this is equal to the original matrix back, right? Just A. So let's now work it out the other way around. I times A is 1, 0, 0, 1 times A, 1, 2, 3, 4. So this is going to be equal to, let's see, 1 times 1 plus 0 times 3, and 1 times 2 plus 0 times 4. Row 2, column 1 is 0 times 1 plus 1 times 3. Row 2, column 2 is 0 times 2 plus 1 times 4. So let's again simplify. Let's get rid of anything that's multiplied by 0, because that's also going to be 0. This is 1, 2, 3, 4. So just as we suspected, this is also equal to A. So again, that's the special property of the identity matrix. You could do this same calculation with any 2 by 2 matrix, with any 3 by 3 matrix, with any 4 by 4 matrix, and find exactly the same thing. So that's the identity matrix. So I think that's all for today. What we're going to do next time is do multiplicative inverse, which is basically kind of like dividing by a matrix. All right, see you next time.